All right, let's solve this problem based on the um, eh, the Exergy, and also based on the second law of efficiency. So basically, this problem is telling us that a heat engine with heat engine receives heat from a source of 1100 Kelvin. So this is a heat source which is at 1100 uh, Kelvin, right? And then it's receive heat at a rate of 400 kilojoule per second. So Q equals to 400 kilojoule per second. Actually, it will be small q, okay? And then there is a heat engine, right? This heat engine, it's basically and it's rejecting heat 320 Kelvin, so which is 320 Kelvin. This is sink, right? And then it is producing some sort of work. That work is output is 120 kilowatt, 120 kilowatt, and the environment temperature is 25 degrees C, right? So first thing is that reversible power and the rate of irreversibility, and the third is that second law of efficiency, right? So what is the reversible power? So to determine the reversible power, first thing we have to determine the reversible efficiency. So reversible efficiency is nothing but the maximum efficiency that we can achieve from this system, right? So the solution, um, reversible efficiency, which is equals to eta thermal efficiency or maximum efficiency, or we can write it reversible, right? Which is equals to 1 minus T low temperature, T high temperature. So if we plug in all those values, eta Th reversible, which is equals to 1 minus, so the low temperature reservoir was 320 and high temperature 1100, 320 and 1100, excuse me, 320 and 1100. So eta thermal of reversible process, which is equals to, if we do solve this, it will be 0.7091, right? So that's the efficiency of that ideal cycle. Now we know that efficiency of that ideal cycle. That means that also we know that efficiency, the definition of reversible, which is equals to reversible workout, right, output divided by reverse Q in, or whatever heat is coming into this heat engine, right? This Q in here. So we know all those values. That means if we plug in W reversible output, right, is equals to eta thermal reversible times Q in. So we just got these values. Eta thermal reversible is 0.7091 times the Q in. We have here 400, right, kilojoule per second, 400 kilojoule per second. So W reversible and output, right? So W reversible and output will be, if I multiply these two, it will become 283.6 kilowatt. Joule per second means that kilowatt, right? I can express this reversible output as in terms of power. So this is number A, right? And this is the answer. And then B asking us that what is the rate of irreversibility. So in the previous class we saw that irreversibility, which is defined by I, equals to the difference between the reversible output, work output minus W useful, right? So we have both of these value. So we just got the reversible output 283.6 and useful work producing by this heat engine 120 kilowatt, 120 kilowatt, right? So basically the irreversibility rate will be 120, that means 163.6 kilowatt. So this is the answer for B, right? And then the 3 is asking us that what is the second law efficiency. So we just derived in the last class that the second law of efficiency, eta 2, we defined it by eta 2, which is equals to W useful output divided by W reversible output, right? So we have the useful output, which is 120 kilowatt, and reversible output we got 283.6, right? So eta 2, which is equals to 120 283.6 equals to 42%, 42.31%, right? So eta thermal equals to, sorry, eta 2 equals to 42.31%. so that's the answer. So we have all of those answer, right? So this is 42.3%, 284 and 164, right? So yeah, so that's all about this problem. Thank you for watching this video, and we'll come back with another lecture.